reaction toward the product. So you want to use a high temperature for reaction 2. Now what happens to the pressure? So what we want to do is again compare the moles of gas reactant to gas product. So note that in reaction 1 we have 2 moles of gas reactants. We have 2 moles of gas product. So does changing the pressure shift the reaction in one direction or the other? Okay, because we have the same number of moles of gas on each side, so changing the pressure should do nothing. Okay, so it doesn't really matter what pressure you use for reaction 1. Now, in reaction 2, note that we have 3 moles of gas reactants producing 2 moles of gas products. So would you want to use a high pressure or a low pressure to increase the yield of product? Okay, you want to use a high pressure. Okay, so again, this is the analysis we can do to use equilibrium to figure out the temperature and pressure conditions for a reaction. Okay, so let's take a look at this next slide. This is the production of ammonia. It turns out that 500 million tons of nitrogen fertilizer produced annually. It actually takes quite a bit of energy to make ammonia. It uses 1 to 2% of the world's energy supply each year. And nitrogen which is produced is either as ammonia, NH3, ammonium nitrate, or urea. Now it turns out that, see, if you can do this, you're going to get your name in about a lot of books. If you can figure out a cheap way to make ammonia from nitrogen, do this nitrogen fixation reaction like plants can do, you can probably retire early and sail around the world with boats. Do that kind of thing. Okay, so anyway, this is the industrial process to make ammonia. So it's called the Hopper process. So it produces ammonia, NH3 from N2 and H2. The reaction conditions are high pressure and low temperature. A catalyst is used, and product is removed from the reaction vessel during the reaction. So let's do the following. Write a chemical equation that represents the Hopper process, and then explain why these conditions are used. If a catalyst was not used, could a higher reaction temperature be used to optimize the yield of product? So what I'd like you to do is to answer question A and B. If you want to do this working with the person sitting next to you, I encourage you to work together. Okay, so for part A, does someone have a chemical equation that represents this reaction? Okay, so our reactants are going to be in N2 plus 3H2 That's going to produce 2NH3. Okay, so there's our here's our chemical equation that represents this reaction. So it says here that, let's see, the reaction consists of high pressure and low temperature. Why would you want to use a high pressure? Yes, we have gases involved, but why high pressure rather than low pressure? Okay, now, see, speed doesn't have to do with equilibrium. Okay, so the reaction rate is different than equilibrium. So using let's say today's principle doesn't tell us anything about how fast or slow the reaction occurs. That's actually a separate question. See, solubility of gas, that has to do with the gas is soluble in, say, a liquid. And there's no liquids here.
Number of moles?
Yeah, so we have a number of moles. Now, how many moles of gas reactants are present? Yeah, so now we have 4 moles of gas reactants. How many moles of gas products are produced? We have 2, so we have 2 moles of gas products. So if we increase the pressure, in which direction will the reaction shift? Yeah, toward the product side. Now it says here that low temperature is used. Now what information do we need to figure out the temperature conditions? Yeah, we need to deal with heat of formation, because heat of formation will give us information about the heat of reaction. So if we take a look in the textbook in appendix, let's see, appendix in appendix 2 for ammonia NH3, that has a delta H of formation of minus 46.3. Okay, so delta H, that's minus 46.3 kilojoules per mole. And then for delta H of formation, that's equal to 0. And then for this one, that's also equal to 0. Then when you apply Hess's law, it's equal to the sum of the heats of formations of the products minus the sum of heats of formations of the reactants. So based on that, is this reaction exothermic or endothermic? Okay, so if you have applying Hess's law, delta H of reaction is equal to the sum of the delta H's of formation of the products minus the sum of the delta H formation of reactants. So let's see, in this case here we're going to have 2 times minus 46.3 minus, let's see, 1 times 0 plus 3 times 0. So delta H of formation is going to be positive or negative? This should be negative. Okay, so delta H of reaction should be less than 0. This means it's exothermic, so that means heat is considered a product or reactant? Yeah, so heat's going to be a product, so let's put heat here. So if we, based on this, why do we need to use a low temperature? Yeah, because by using a lower temperature, that's going to, if we remove heat, that's going to shift the reaction toward the product side. A catalyst is used. Why is a catalyst used? To speed up the rate of reaction. So since we're using a low temperature, lower temperature decreases the rate, but a catalyst will increase the rate. Now, what's the effect of pressure on this reaction? Will it increase the rate or decrease the rate? Yeah, so increasing the pressure should increase the rate. And it says here that product is removed from the reaction vessel during the reaction. So ammonia is being removed as it's produced. So what is the effect of removing the ammonia? Yeah, so by removing the product, this is going to shift the reaction toward the product side and increase the yield. Okay, so all these reaction conditions serve to increase the yield and then make the reaction go fast enough where it's not too expensive to do this reaction. Okay. Then it says if the catalyst is not used, could a higher reaction temperature be used to optimize the yield? Okay, so if you increase the temperature, is that going to increase the yield or decrease the yield? Yeah, so increasing the temperature or adding heat is going to shift the reaction toward the reactant side, and that will decrease the yield. Okay. Okay, so we're going to do some calculations involving this equilibrium constant. So based on the numerical value of the equilibrium constant, we can calculate the amount of reactants and products present under equilibrium conditions. So here's a problem from the text. This is problem 15.72. It says in a certain experiment, this is what we look at. A student starts with 0.862 atmospheres of N2 and 0.373 atmospheres of H2 in a constant volume vessel at 375 degrees. So note that I consider this high temperature, but industrially speaking, this is actually a pretty low temperature. Calculate the partial pressures of all species when the equilibrium is reached. So this is how you would set up. It's like doing a stoichiometry problem. So here's our balanced chemical equation. This is the initial amount of each reactant we have present. 0.862 of N2, 0.373 atmospheres of H2, 0 amount of NH3. Now, since this is an equilibrium reaction, we do not know how much of the reactants react. So we're going to say that X amount of N2 reacts. Okay? If X amount of N2 reacts, 3X amount of H2 reacts. Now, why is it 3X? Yeah, because we have that 1:3 ratio of N2 to H2. And note that 2X moles of NH3 are produced. Okay, so again, these first two lines are really like the same thing as doing a stoichiometry calculation. The only thing we are doing is that for the amount that reacts, we're using X. So at equilibrium, we have 0.862 minus X for N2, 0.373 minus 3X for H2, and then 2X for NH3. Once we get to this point, now again, this is the same as we were looking at excess and limiting reactants here, so the amount of equilibrium is really the same thing we've done before in Chem1A. Now we can plug in these equilibrium amounts into our equilibrium constant expression. So the equilibrium constant, 4.31 times 10 to the minus 4, is equal to 2x squared. Okay, so that's the NH3. We square it because of the 2 coefficient, divided by 0.862 minus x times 0.373 minus 3x cubed. And then, this is the math part. This is the fun part. Solve for x. Note that this is not fun. If you have to do this by hand. Now, what we're going to do is we can make some assumptions here. Note that this equilibrium constant, 4.31 times 10 to the minus 4, is small. So based on this numerical value, are we going to see more reactants present or more products present? Yeah, we're going to see more reactants. Now, based on the value, will we see a lot more reactants present or a little bit more reactants present? Okay, so we have 4.31 times 10 to the minus 4. So we're going to see a lot more reactants present than products, or just a little bit more reactants present than products. Is this number small? 10 to the minus 4? Yes, that's a small number. So that tells us that we should see a lot more reactants present than products. So when we look at this equation, Let me write it on the board. We have 2x squared divided by 0.862 minus x times 0.373 minus 3x cubed, and that's equal to 4.31 times 10 minus 4. Now, since this number is so small, and you just said that there's going to be a lot more reactants present than products, that means that the amount of x which reacts should be big or small. Yeah, this should be very small. So since x is small, we can say this is approximately equal to 0. And that means that this is going to be approximately equal to 0. So this simplifies to this equation. We have 2x squared is equal to 0.862 times 0.373, and that's equal to 4.31 times 10 minus 4. And now it's really fun to solve for x, because instead of solving this complex, what is it? It's we would have x cubed times x is x to the 4th. Well, that's a, I don't want to solve it. I don't think you want to solve a polynomial. Okay, so we can do that